of all, I would like to say that it's a great honor to me to be among the first International Excellence Fellows, and also to open these International Excellence Talks. I'm very thankful to all the people who helped me, who nominated me, first of all, and who helped me and supported me during this day. That was a great time, and it will certainly be a memorizable event for all my life. Today, I'm going to tell you about the research we've done in the last years in the area of treating cancer. And this is how my 14-year-old son, Roman, imagines cancer. Every child knows that cancer is a problem. It's a great problem which causes death and loss. And I'm sure that everybody of us would like to contribute to the efforts of many scientists and researchers who direct their efforts against this disease, against this very deadly disease. Some of these efforts are focused on using electromagnetic radiation. This is another piece of art. This is a mosaic on one of the buildings of National Cancer Institute of Ukraine. And the artist was going to show here in the allegorical form how scientists and clinicians fight cancer. And you can see the radiation in hands, dealing with the evil. In fact, electromagnetic radiation of high energy is very widely used in clinical oncology. Since the middle of last century, scientists found that high energy rays, like X-rays or radiation, which is called by radioactivity, gamma rays, they can destroy cancer cells. And this is now a fully established treatment modality in clinical oncology, which is very successful. In combination with chemotherapy, the cure of many types of cancer can be achieved. However, whatever it is successful, of course, but it has also an issue. Everybody knows that high energy rays like X-rays or gamma rays, they are damaging themselves. They can damage not only the cancer tissue, but also healthy tissue. In fact, this radiation can even cause cancer. What about low energy light? For example, the electromagnetic radiation, which can be detected by our eyes. This is a visible light. Well, if it's high intensive, like intensive laser light, it can be used in cancer treatments, evaporating or eradicating, or scientists say, ablating cancer. It's not as efficient. And you might think that using the light with lower energy would even be less efficient and useless, but it's not. In fact, there is another treatment modality, which is called photodynamic therapy, which is well established as well. And it is based on using visible light, low energy, red laser light. This treatment modality is based on the use of the so-called photoactivatable compounds. They are called photosynthesizers. These compounds are known to humans for ages. By the way, if you meet this plant somewhere in the wood, walking in the wood, please keep away from it, because when you touch it, you can get severe sunburns. This is because this plant contains compounds which are photosynthesizers. There will be a little bit chemistry today. The compounds look like that, so they can absorb the energy of photons and then convey this energy to oxygen, which is always in our tissue. And this is oxygen, which becomes very aggressive. It's called singlet oxygen, which causes these sunburns. The idea to use such compounds for cancer treatment and treatment of other diseases emerged very long ago. I was fortunate to find the very first paper where this idea was formulated. This is from Oskar Raab, who worked at the beginning of 20th century in Munich. He and his professor, Dr. Tepiner, discovered that some compounds, like those I'd shown you on the previous slide, they can be excited by light, by sunlight, and this can lead then to destruction of microorganisms. They worked with infusorium. It's fun that in some places, and several places in the paper, Oskar Raab is thanks not only his professor, Dr. Tepiner, but also good weather, full of sunshine, which helped him to make this discovery. Since then, this discovery was developed to a full established treatment modality. I told you it is called photodynamic therapy. So it uses the low energy light, red light first of all, delivers it to the cancer tissue. Other diseases, infection diseases can also be treated by this therapy. And then the photosynthesizers, which are administered to patients, they are excited and then convey the excitement energy to oxygen, which destroys the cancer tissue. In the next several slides, I will illustrate in a short cartoon how it works. So the photosynthesizers, which could be called also photodynamic PDT agents, they are first administered to the patient. Then it's important that they should accumulate in the cancer tissue or in the lesions. And then they irradiate the tissues with light. And because you can focus the light very precisely, this treatment modality is so precise and selective. You can direct the light to the cancer tissue, and in such a way, do not touch, do not leave the whole body intact. So I said this treatment modality is very efficient. It is officially recognized and approved in many countries, including Europe and USA. And inspired by success in this area, we wanted to contribute as well with our ideas, expanding this treatment, expanding this approach. And this is where we introduced our ideas. We knew, as a chemist by education, I'm a chemist, we knew that there are many compounds, many compound fragments, which can change the structure upon irradiation. So they can exist in two or several different forms, photoforms, which can interconvert between each other when you irradiate the compound with the light. When you irradiate with the UV light, it exists, these compounds exist in one form. With red light, with the light with different wavelength, they exist in different form. So when structure changes, one might expect that the property could also change. And we hope that by incorporation such fragments into existing drugs, we can control the biological activity, switching them on and off. We were particularly attracted by certain kinds of certain chemical type of these photoswitches, which are called diaryl ethylenes. They were not only efficiently photoswitching, so you can toggle between two structures, and we hope between two biological activities, but they are also stable to degradation, and they have high thermal stability. Each photoform has high thermal stability. This suited particularly well to our idea. And the idea was to incorporate such a photoswitch into biologically active peptide. Peptides, natural and artificial, are very diverse. They have very different biological activity, and there are anti-cancer, antimicrobial, and many other peptides which are now developed also as drugs So we wanted to incorporate the photoswitch in the way which is schematically shown here on this slide. So the peptide molecule is schematically shown in blue. We can chemically connect it to the photoswitch, which is shown here as a star. And then, as you can imagine, when we switch the lights, the photoswitch can change the structure, and these changes can be then conveyed to the peptide molecule. And we hope that in one photoforms, this molecule would be not acting, and the other photoform, which would be generated by light, preferably by red light, tissue benign red light, they could be active. To realize this idea, we certainly had to modify the known photoswitching fragments. You know that peptides and protein in the whole are composed of the amino acid residues. So we had to convert a photoswitch fragment into amino acid surrogates. So chemically we did that. We attached a carboxylic group from one side, an amino group from the other side. So you can see this is now amino acid, carboxylic acid, and could be incorporated in peptides by standard ways. Some of the peptides could be synthesized automatically by peptide synthesizers. So these were building blocks which we synthesize in several different forms suitable for incorporation in peptides. Then we choose the peptides. I remember the discussions, internal discussions, which peptide to choose. And actually it was spontaneously, I should say. So we choose the peptide which we knew very well. And this is very well known globally antibiotic, peptide antibiotic. It is called chromicidin S. This molecule is interesting from many sides. I can talk about it for ages. This was the first antibiotic, one of the first ever discovered. The first antibiotic discovered in Soviet Union. S means Soviet. It was discovered by prominent microbiologists Gauss and Brashnikov in 1942. Since then, it was widely used as antibiotic. It saved many lives. However, it was toxic when it is administered systemically, so it could be used only topically. So we thought this is an ideal peptide template to modify it by our photoswitching building blocks and to make it photosensitive, photoswitchable. We analyzed the structure and thought that the photoswitching ethylene fragment fits well to the corner, one of the corners of this beautiful molecule. Like is shown on this slide, the photoswitching fragment is highlighted in red, or here, or in another part. So we synthesized several molecules, actually many molecules, which contain photoswitch, and then started to test them. We were pleased to find that the biological activity of this antibiotic, the antibiotic activity against bacteria, first of all, was photoswitching. We did several proof of principle experiments, and one of the experiments is illustrated here. So we put the compound in the less active form. We called it off form or closed form, which is here, together with bacteria and the broth, the media in the Petri dish in dark, and then irradiated the Petri dish with the light through a mask with a certain pattern cut. In this case, KT logo. So in the places where the light reached the Petri dish, it switched on the compound and the bacteria colonies did not grow. In places where it remained inactive, the bacteria colonies happily grown. So we saw the pattern in the end. So we did even artwork with this. This is, by the way, Mona Lisa, if you do not recognize. Arguably, this is one of the most unusual Mona Lisa portrait replica made by bacteria. So in this case, we irradiated Petri dish through a semi-transparent Mona Lisa portrait and got a portrait made by bacteria. Certainly, we went on to serious scientific experiment exploring this photoswitching, and first of all, the prospect of using these compounds as therapeutic agents. So this is one of the scientific slides where you can see that the photoforms on and off of three compounds are very different in activity against bacteria. Minimal inhibitory concentration, MIC, is very different. It's shown here in green for the active compound and red for the non-active. In its active form, these compounds are almost as active as gramicidin S itself. GS is shown here in gray, but the other form is less active. So we could find the concentration of these compounds which could be systemically introduced. So this was the first time when such a prominent and renowned antibiotic got the second life and could be introduced directly to the patient systemically. So certainly we studied cancer cells and we discovered that photoswitching works here as well, very well. So different photoforms of our compounds were very different. One of them on form were destroying cancer cells and the other form was safe. So after that, we decided to go to the experiments in vivo. But you probably asked me how we would deliver the light. For example, when cancer tissue is deep inside the body. Well, this is not a problem. I told you that there is well-developed similar technology, which is called photodynamic therapy. It was approved many years ago, and now the whole industry exists, which offer many devices for light delivery. Now, light delivery is now not the problem for almost all parts of the human body. So we just had to use them. Using them and using the synthesized compounds, we did many in vivo experiments on animals. We were especially pleased to find that the photoswitching works in vivo as well. So at that time, we believed that this technology could be used in vivo and ultimately in humans for treatment such diseases as cancer. So in cancer models, in these mice, we saw that the tumor shrunk, like shown here, when we administered the compound. It's called LMB-001, one of the compounds we synthesized, and shine light on the tumor, while in the control in grown and the mice, of course, died. We continue to do these experiments, and we sincerely believe that sooner or later, of course, very soon, these compounds become smart drugs. They will be safer than traditional analogous drugs because, as you understand, we can administer the compound in the less active, non-toxic form and activate it by light specifically only in the lesions in cancer tissue, for example. So as Anna said, we dared to establish a company which is called Humabiotics, analogously to antibiotics. I think we have a great team. Tim Schober is now a CEO. He is very enthusiastic and very excited about the technology and did much for that. And also other team. This company enjoys the support of KAT and many other organizations which believe in our idea. Thank you for your attention and to express my gratitude to all the people who collaborated in this area. The team from Karlsruhe, Professor Anne Ulrich and her group, and also my group in Kiev. Only the tiny fraction of people who collaborated fit to this slide. There are many students, many other collaborators who contributed to this area, and I'm certain will contribute in the future. Thank you very much again for your attention.